Okay, good evening, everyone, and welcome to the IMA Northwest Branch talk on probability, risk and randomness. Our speaker this evening, Andrew Pargeter-Davies, has many years' experience teaching mathematics in secondary schools, alongside responsibility for Key Stage 3 mathematics and A-level mathematics teaching. If you have any questions during his talk, please could you pop them in the question and answer section, and we'll put these to Andrew at the end of the talk. So I'm delighted to welcome Andrew this evening to talk to us about probability, risk and randomness. Thank you, Andrew.
Thank you very much, Rachel. Thank you everybody for giving up some of your no doubt very valuable time from whatever your job is and stuff and responsibilities to take time out to listen to me this evening. I'm just checking. I had a vague dread that I would be able to see people's how many people are attending this, and I'd be able to watch your numbers click down as people decided that this wasn't the talk for them, but I can't actually see that, so I'm very relieved about that. Okay, so hopefully I'll start off just by telling you a tiny little bit about myself and my background just for a minute. I went to school in Stockport in Manchester. I did a maths degree, mostly specialising in pure maths, and then trained as a teacher, both at Leeds University. And since then, I've taught in a variety of schools, mostly in state schools until 2013, when I moved to Manchester Grammar, where I still am. And I'm currently responsible for maths in year 12 and 13. Okay, so I should say the next, I'll talk about my relationship with probability and where I've come across it. I should say the very next slide that I'm going to bring on, if you have a nervous disposition, you may want to steel yourselves. It does feature a picture of me as a student. I've shown this to a few colleagues and they actually refuse to believe that it is me. So I'm really apologise for this. So my experience of sort of probability and statistics as a student was back pre-national curriculum days. So I did a very little bit of probability up to age 16. I then took statistics as part of A-level maths and further maths, and I did quite a lot of probability and statistics in my further maths course. It was in sort of a good old mix and match days when we could choose units, and we did kind of the most probability and statistics that we could do. So I met quite a lot of sort of probability there at A-level. I did a compulsory course with statistics and probability in my first year at university. And then my only other real experience of probability was in my third year at university. I did something called probability measures. I at that point thought pure maths was everything, and I sort of bailed on statistics and probability and applied maths as soon as I possibly could. But I was kind of slightly intrigued at this idea that probability came back in what I thought of as an extremely pure course. And anyway, I then kind of went off to train as a teacher, came across a national curriculum and got into my current career. So where have I met statistics and probability as a teacher? Again, I apologise for the photograph. So this is me this week. People do claim that that's unrecognisable, but I think that's not particularly kind. So now I teach probability as part of handling data to year 7 to 11. I teach A-level maths, so I teach the sort of usual bits of probability and probability distributions and things like that. So normal distribution, Poisson. I do further maths A-level as well. And at some point in the past, I have taught A-level statistics as well, which, to be honest, didn't really do very much more in terms of probability. It did quite a lot more in terms of probability distributions and statistics and things, but not much more on actual probability. Okay, so as we're sort of aiming this talk at teachers, probability is a compulsory part of the national curriculum in maths from primary school onwards, and it appears as a compulsory part of A-level maths. It's actually not compulsory, I think, in further maths. You can avoid it if you want, but every time I've taught further maths recently, it's involved a probability and statistics component. And this is the point where I start to sort of have a few worries about how we do statistics, about how we do probability, because it often appears divorced from anything realistic, and it's sort of isolated from a lot of the rest of maths. I mean, we tend to teach a little unit on probability. We talk about equally likely events. We talk about things being independent, and then we move on to something else. And let me give you an example of what I mean about it being divorced from things. So I looked up how probability appears in the national curriculum as it is. This is the Key Stage 4 notes on probability that I Googled from the gov.uk website. The particular bit I was looking about was things like calculate the probability of independent and dependent combined events, including using tree diagrams and representations, and know their underlying assumptions. It all sounds very good and like we're going to do something really exciting. And then when we sort of think about what it actually boils down to us teaching, what we're actually aiming for a lot of the time is that our students should be able to answer questions that look like this. Okay, if you troll back through GCSE, which is most students' experience of probability, there are an awful lot of picking sweets and marbles out of bags. So Boris has a bag that only contains red sweets and green sweets. He takes at random 2 sweets from the bag. We're losing students already there, because the obvious answer is look in the bag, pick the one you want. And I'm not saying that this sort of question has no place in teaching, but we have to sort of realise that it's a very artificial situation. It doesn't really engage our students. It doesn't have any connection to their real life. And oddly, I think this sort of focus on these kind of equally likely events and things that we can nicely calculate can lead to some misunderstandings. So I'm going to start off now, or carry on, looking at a couple of misunderstandings in probability. One of them is from my own experience, and one of them is a famous one, which I'll do in a little detail. So the first one that I'm just going to mention now and then come back to is a conversation I had with a year 11 student. This happened probably, it must be nearly 20 years ago now, but it has stuck with me. I swear that this was an absolutely genuine conversation I had with a year 11 student, probably around February or March of year 11, and not necessarily the best student at maths, but nevertheless quite engaged. And I asked them the following question: what are you going to do when you finish your GCSEs? It wasn't a student in my maths group, it was somebody that I was doing a revision session with, and we're just at the end of the session. So I was asking various people sort of questions like this: what are you going to do when you finish your GCSEs? The reply floored me. I'm going to win the lottery. And I promise you that that's the reply. So not quite knowing how to respond to it, I said, isn't that quite unlikely? Thinking I could lead it on to, that'd be nice, but maybe you should have an actual plan as to something that might, actually be sort of likely for you. And the response to that was, well, you either win or you don't. It's a 50-50 chance. And again, obviously somebody who's completely misunderstood the idea of equally likely outcomes there. And, I'm sure that was an excellent teaching point, but by the time somebody's approaching the end of year 11, perhaps that's kind of a little bit ingrained in them. I did engage with the students and try and explain that it wasn't. And I think that by the end, they realised that probably trying to pass their GCSEs and potentially sort of go on to college or university might be a good plan, because they probably weren't going to win the jackpot in the lottery. I don't believe they ever did. So unfortunately, I suspect they're still working somewhere. Okay, but misunderstandings in probability are not limited to students in schools, and they can arise for all sorts of reasons, some of them good and justified, and some of them less so. I'm sure that many of you will have heard something, if not in detail, about the sort of case I'm going to describe now. So let me introduce you first to an interesting person. Okay. Marilyn Vos Savant is an American writer. She was born in 1946, and in the 1980s, she achieved absolute worldwide fame when she was listed in the Guinness Book of Records as being the person with the highest IQ in the world. And there was lots of media coverage, the world's smartest person, that kind of thing. And to get into my criticisms and my thoughts on IQ tests would take a whole different talk, and I probably don't know enough about the background of testing like that, but whatever, that's how she was billed in the media. Now, she's an interesting character in that she didn't actually have a college degree. She's American, sorry, I should have said. She didn't have a college degree. She'd done some work in college and never graduated. She'd worked for a while in a family business. She'd been married. She moved to New York to work as a writer and journalist. And she, on the back of being good, being sort of supposedly very clever, she did a column called Ask Marilyn. And in 1990, she published one of probably the most famous sort of mathematical problems that there's been in the last 30 years. She published something that's now called the Monty Hall problem. And Monty Hall was a game show host in America. I've kind of simplified the version a little bit. In the original version, there are 3 doors, and there's a car behind one, and there is a goat behind the other 2. But I've simplified it slightly. So the version I sort of thought we'd look at is there are 3 boxes. 1 contains a prize and 2 are empty. You choose a box, but don't open it. So you can basically think that you pick a box, you put your hand on it and say, I'm going to pick that box. Okay. Monty Hall, who is hosting the show, opens one of the other boxes and shows you that it's empty. Do you keep, and then says, you have the opportunity to swap. Do you want to keep the one you've got, or do you want to swap to the remaining unpicked box? And Vos Savant's solution to this problem said that you should always switch. So you should always switch from the one you chose originally to the other box that's remained unopened. And she said, switching doubles your probability of winning. Okay, so she published that. It was an interesting problem. She thought it would be a good source for a column. She received, I believe, according to the internet, over 10,000 responses. And this was in 1990, so they were probably actually handwritten and posted rather than email. It wasn't a case of firing off something quick on social media. It was an actual sort of letter or something like that. She received over 10,000 responses disagreeing with her solution. Over 1,000 of the responses came from people with PhDs in some branch of maths, disagreeing with her. Okay, I've picked out 3 of the responses, okay? And I just want to sort of share them with you and then sort of talk a little bit about people's reaction to that that solution. So the first one, you blew it, and you blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There's enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame. Okay, not that anybody's talking down to her there at all, but the next response. May I suggest that you obtain and refer to a standard textbook on probability before you try to answer a question of this type again? And the last one, which I was actually sort of so shocked by that I had to read it twice. I did think twice about including this because I found it sort of quite upsetting almost. Maybe women look at maths problems differently than men. And it's just, I don't know, an awful way. All of those were so belittling. And if you read through a lot of the responses to her, they were generally, they didn't really give an alternate solution a lot of the time. They just took the view that, well, it's obvious she's wrong. There are 2 boxes left, so it's a 1 in 2 chance, rather than they're both the same. And this is something that if you're talking about things with students, maybe you can sort of use this in 2 ways. It's quite good to sort of bring this in and explain this problem. Is it possible that Vos Savant was being mansplained, that people didn't like it because it was a woman who was saying something? People didn't like the solution because it offended their common sense. And maybe all those maths PhDs didn't like somebody who was explaining something they didn't agree with, and they were having it explained to them by somebody who didn't have an academic qualification. So there's all sorts of issues that sort of, I suppose, verge into the kind of PSHE and equality of opportunity and all that kind of thing, and how we treat people, how we respond to people. I mean, it's essentially like a social media pylon would be today. I presume it just took place more slowly. But, you know, this is something where we can actually discuss the problem. Incidentally, if you're interested in doing with a class maybe the actual solution, the solution can be got to the Monty Hall problem by looking at the most powerful mathematical technique known to humankind, which is obviously the tree diagram. So this tree diagram sort of explains it. Hopefully you'll be able to sort of see a copy at the end on the video if you want to look at it. The best way of doing it is to label your boxes X, Y, and Z and say, okay, you pick X. You can always say that you've picked X to start with, because if not, just label the box that you have picked X. Okay, so the probability that the prize is in one of those 3 boxes is 1/3 in each box. Okay, now if the prize is in box X, the host can choose to reveal Y or Z, and he could pick those with probability of half. Actual fact, it doesn't matter how you split up the probability of what he picks them, it won't change the decision. If the prize is in Y, you know that you're going to be shown an empty box, so the host must be showing you box Z with probability 1. And if the prize is in Z, the host must be showing you Y. So using our usual way of working with tree diagrams, we can work through this. Okay, if you stick, you only win for these 2 branches where the prize was in box X, which is a total of 1/3, 1/6 plus 1/6. If you switch to the other box, the other unopened one, so if it's in X, you'd switch to Y and you would win with probability 1. Okay, so you'd lose there, but you'd win if you switched, probability 1/3. And if the prize was in Z, you'd win with probability 1/3. So your chances of winning if you switch are 2/3. Okay, that's so apparently what Marilyn Vos Savant was saying. But is that actually the solution? Sorry, I've got an extra slide in that I didn't need. I duplicated that one. Okay, we've made an assumption there that the host knows where the prize is. If the host doesn't know where the prize is and just opens one of the other 2 boxes at random, there are actually 3 things that can happen. Okay, we can win, we can lose, or the host can accidentally open the box where the prize is. And in that case, if the host has no knowledge, then the people who criticised Vos Savant were right. The probability stays the same. The probability of you winning is 1/3 each time, but the probability that the host opens the box and reveals the prize is also 1/3. But it's interesting, Vos Savant commented that almost none of the 10,000 responses she got were querying her initial assumptions. They all tried to use some very powerful or sophisticated technical theory. Bayes' theorem was often quoted, or they just appealed to common sense. Okay, almost nobody said kind of, well, it depends on your assumptions. But this one is a good thing to do, that you can talk to your students about the importance of clarifying your assumptions when you do a problem. If we're not exactly sure of what's happening, then it can have a big impact on the answer. And Vos Savant published, I think, 2 other columns in that year for the magazine that she worked for, both of which, the first one clarified her assumptions, and the second one basically restated her case and said, no, I'm right. And I think in that sense, although some people since have sort of criticised her first column for not being sufficiently clear, she did provide a sort of excellent model in sort of actually sticking to what she was saying and not being intimidated by people who were just attacking her, really, because it didn't agree with their assumptions. Okay, so I will leave Monty Hall there. If I can now return to talking about, well, this is called probability versus risk. I'm actually going to return to my conversation with my friend in year 11 of 20 years ago. If you remember, what were they going to do? They were going to win the lottery because it was a 50-50 chance. Okay, and then I started thinking after that conversation, why would there particularly be misunderstandings with the lottery? And I did some reading about this, and one of the things that I discovered was that in our heads, we give greater priority to events with greater consequences. So winning the lottery is an important life-changing event, so it's kind of important. And that's what I mean by risk, that instead of having a probability scale of it goes from, impossible to certain, in our heads, our more intuitive scale goes from unimportant to life-changing. And when we look at events, we tend to think of them in terms of risk rather than the actual probability of things, or of importance, if you like. And in a way, this is kind of part of the human need to find patterns in things. So it's kind of like we like to see things repeating. We want to read patterns in things. We like to know things are predictable. We don't like randomness. And that kind of is going to tie into like the next little bit of my talk, which is going to be about randomness in things, because the human mind does not like things to be random. And we often think about risk or reward when we use language. Maybe we should be clear about what we're talking, not say we have chance of things happening or the risk of things happening. Maybe we should stick to our more formal language when we talk about things. But let me talk now for a little bit about something very random. Okay. When I first started teaching in the 1990s, and I was teaching probability, especially to year 7s and 8s, I used to love doing probability as the first thing I did in September, because it allowed me to do something a little bit practical with students. And this is the activity, and you have to set this for homework. You can't do it in class. I'm sure some people will have done this with groups before, but this was one of my favourite activities. Flip a coin 20 times and write down the sequence of heads and tails you get. What I used to do was to get the students to write them down on a piece of paper and then hand them in, sometimes anonymously, sometimes with names on. And you have to be careful not to embarrass students, but it's always possible to tell at least one student who's thought, Mr. Davies is a sucker. He's got me doing this at home. He's not going to know if I've faked this. I don't really have to spend the time doing it. I can just write down heads and tails 20 times and he'll never know. Okay. And I used to sort of point out the flaw in that argument to people without actually revealing that I knew who had done it. So let's compare 2 potential students who would have handed something in. Student A would have written a sequence of heads and tails that would look like that. And student B would have written a sequence of heads and tails that look like that. Okay, the thing I'm assuming that many people here will immediately think student B has cheated. Okay, the important thing to student B is probably something like, well, there should be about the same number of heads as tails, or something like that. Or even worse, once I've had a head, the coin will want to do a tail afterwards, because many younger students seem to have this idea that objects like coins and dice have a memory and they want to kind of even things up. It's like they've been especially trained to be fair and give even results. But it's often quite hard to tell students sort of how we know that that top one probably was done genuine. I mean, as you all know, there's nothing that says that that bottom student B didn't do it genuinely, but it's very unlikely that they would have got such a nice sequence of head, tail, head, tail, head, tail, head, tail, head, tail. Okay, that's not likely at all. And perhaps something we could do with students, which is a little bit off the exam specification, but which many students in my experience find interesting, is to talk about what it actually means for something to be random. How do we know if a number is random? If we've got a big list of numbers, how do we know that they're random? What's random? And more importantly for us, what's pseudo-random numbers? So a truly random number is really, really quite hard to generate. I'm going to sort of look at how we can get some in a minute, and indeed I'm going to sort of show you where the world's most random number comes from, which is something that you could possibly share with sixth form students. I find them quite interested in that. But when we look at tables of random numbers, they're very often not actually random. So if we have a list of random numbers that we find online or in a formula book for A-level maths teaching, they're probably pseudo-random numbers. Okay, pseudo-random numbers passed some tests for randomness. So things like if we've got numbers that contain the digits 1 to 0, you know, the expected frequency for every digit will be the same and things like that. If anybody's come across the concept of normal numbers, which again, I very nearly didn't get this talk finished because I came across the concept of normal numbers when I was doing some research about 2 weeks ago, and I got so interested in it that I just stopped everything and started reading about them. So please do look them up, that's fascinating. So these pseudo-random numbers will pass all these tests, what I might call the probability tests, but they can be predicted if you know an algorithm in the seed, so the initial input. So somehow there's a formula generating them. And for purposes of things like, say, encrypting a bank account, that's not sufficiently random, because all it would take is somebody to steal the algorithm and the seed, and they could reproduce your pseudo-random numbers. So, you know, they may be good enough for somebody doing a generating a random sample for an A-level exam, but you maybe wouldn't want to bet your entire savings on them. These days, we generate properly random numbers from physical phenomena. So what we actually do is we set up something like a digital thermometer that reads the temperature to 4 decimal places. Okay, temperatures fluctuate all the time. And we take a reading every 5 minutes, and we take the 3rd decimal place or the 4th decimal place in the fluctuations. So something like that, where we take a random digit out of something that's physically read. But it's really hard to prove that these are actually random. Again, they'll pass the same sort of probability tests, that digits occur in the right sort of proportions and there's no patterns, so the same sort of nice little sequences don't reappear, but it's very hard to prove that they are random. Okay, so what do I mean by sort of randomness? I'm going to go on to try and sort of generate a random sequence in these probabilistic sense that I've just been talking about. So first of all, we might say what we need is that every digit has an equal probability of being in the sequence. I'm going to talk about sequences of just binary numbers here, just use 1 and 0s. Everything I'm saying applies to sort of base 10 as well. It's just I would have needed to write a longer number for it to make the point. So every digit has an equal probability. Well, Unfortunately, that's true in that sequence, which certainly isn't random. So every digit having an equal probability of being in the sequence or the same frequency doesn't work. So what I'm going to say as a criticism of that sequence is that, well, every time we've got a 1, it's followed by a 0, and every time we've got a 0, it's followed by a 1. Well, maybe if we expand that so that every digit has an equal probability, and that, say, a 1 has an equal probability of being followed by a 1 or a 0, and a 0 has an equal probability of being followed by a 1 or a 0. So every digit has an equal probability. Every digit has an equal probability of being followed by any other digit. Well, the problem with that is that that sequence fulfills those criteria. 1, 1, 0, 0, 1, 1, 0, 0, because 1 and 0 appear in equal frequencies, and half of the 1s are followed by 1s and half by 0s, half of the 0s are followed by 0s and half by 1s. And again, we've got a very unrandom sequence. So I hope you would agree that I could carry on sort of doing that kind of thing, and all I would do is I would make a sort of slightly longer chain of things. So I'm sort of chasing my tail here and not getting anywhere. So I want to sort of introduce you to an idea of looking at how complex a sequence is. So the idea of algorithmic complexity. So one idea for seeing how complex a sequence is to look at the size of the rule or the algorithm needed to generate it. So in other words, you can think about, if you've got a sort of infinite sequence, how long is the computer code or the recurrence relation or something like that that you need to generate it? The longer it is, the more complex the sequence is. And a sequence could be said to be random if it can't be generated by an algorithm shorter than itself. Okay, if the most concise way to express a sequence is just to write down the sequence, then it's random. There's no rule for it. Now, for an infinite sequence, that means that there shouldn't be an algorithm for writing it down at all, which is why it might be very hard to actually produce one. But I'm hopefully going to, an infinite sequence can be random only if there's no algorithm to generate it at all. What I'm going to try and do, I hope, is sort of display a few of these algorithms for the things we've already done. So that thing, 0101, could be generated by an algorithm that looked like that. Okay, U1 is 0, so the first term is 0, and the n plus 1th term is 1 minus the nth term. Okay, that generates that quite succinctly. So a very small algorithm for a very regular non-random sequence. Something else we could do if we just got a repeating pattern. So that one is generated by something like that. We just list the first 4, 0, 0, 1, 1, and then we say that the n plus 4th sequence is the same as the nth. So the 5th term is the same as the 1st, the 6th term is the same as the 2nd, and so on. So anything where we've got any sort of recurring pattern, we could just do something like that. So we can, those are the sorts of things I mean by an algorithm. So are there any sequences or numbers which cannot be generated like this? Okay, the answer is obviously yes, otherwise I wouldn't be here giving the talk. But to get there, I'm going to have to take a diversion into what people who know me will tell you is one of my favorite things in maths altogether. Again, some really good teaching points, both mathematically and socially related to this, something I often use with sixth form. I'm going to talk to you very briefly about Turing machines. Okay, not in any massive, I'm going to show you one slide of detail which you can pretend isn't there if you don't like it. Turing machines always gives me an opportunity to talk about Alan Turing, who is one of my favorite mathematicians. Not only obviously did he work at Manchester University, but I think he's also, despite the sort of big acclaim and sort of statues and being put on a banknote and all that kind of stuff, I think he's on a banknote. I need to check that. He's very underappreciated. When we know him now, if you mention him to people, they go, "Oh, crack the Enigma code." But he did so much more than that. He was the first person in mathematical biology to explain how patterns in animals occur. So how do zebras and tigers have stripes, and how do leopards have spots? Essentially, as I understand it, they're because when they're developing in the womb, there are two chemicals that diffuse from one place, and it's the kind of overlap patterns that they get. That's about as much detail as I know. He found the connection between the Fibonacci sequence and pine cones. If you don't know that, that's worth looking up. It always fascinates students. And he was, in general, just a really fascinating man. You know, did loads of stuff in all sorts of different areas of maths. What I'm going to look at now is the thing that sort of made his name originally. And he started to come up with this idea when he was a student at Cambridge in the early 1930s, I think. So he came up with the idea of a Turing machine. At that time, there were no computers. He was interested in answering a question which was current at the time that said kind of what numbers can be computed? What's a computable number? What numbers can be evaluated? And in his very logical way, Turing said, well, a number is computable if it can be calculated by a machine. But there weren't any machines that he could work with. So he invented the Turing machine, an imaginary machine. If you don't know it before, the way he imagined it was he imagined an infinitely long paper tape that was divided up into cells that he could write a digit in, a read-write head, which is basically like a hand that's moving along the tape, and it could write a symbol in a cell or rub one out, and it could move left and right. And then you would have a set of instructions to tell the Turing machine how to move. The next slide is the one you can skip if you're of a nervous disposition as far as lots of symbols go, because this is the actual definition of a Turing machine. I rarely put this on the board for anybody to see, but I like it too much, so I'm afraid you have to suffer it tonight. Okay, a Turing machine is defined as a septuple, so there are 7 elements to it. So M is a Turing machine, it has to have all of those things, and then we can define what they are. So Q is a set of states. Okay, think of those as being like the line numbers in a computer program: state 1, state 2, state 3, state 4. Each state gives it something to do and then tells it to move to another numbered state. Gamma is a set of symbols that can appear on the tape. So it might be just ones, it might be ones and zeros, it might be all the digits from 1 to 9. You can pick your own set of symbols for it. B is the blank symbol, so you could just leave it blank, or you could write a B, or you could put an X in that cell or whatever. Sigma is the set of input symbols, so you're allowed to use some of the symbols. It might be all of the available ones, it might be a subset, but they're what you're allowed to have written on the tape before it starts. Delta determines the the symbol to write, the head movement, and the next state. So delta is what's called a transition function. It reads the tape, it reads what's there, and it tells the read-write head what to do. Either leave it, overwrite it, or blank it and move left or right to the next cell. So that's actually the thing, you usually see that written out in a table. That's the thing that would look most like a modern computer program, is that little bit. And Q0 is the initial state, so the initial arrangements of things on the tape and where the head starts. And F is the set of final states. Okay, so Turing invented all of these things. And each Turing machine, you can write a program for it and it will do a certain thing. So there are lots of different Turing machines. Okay, that was sort of very clever. That was absolutely original thing to do in his time. Turing went one step further and defined something called the universal Turing machine. Okay, and what he realized was it's possible to list all Turing machines, or it's possible to give each Turing machine a number. Because all the symbols and the sets of things are finite, you can go through all possible Turing machines. So you can have Turing machine number 1, number 2, number 3, number 4, number 5. There'll be an infinite number of them, but you can code them in some way to give them an order. Okay, that means, okay, set is countable, we can give a number to every Turing machine. Turing then realized you can create a Turing machine whose input is a number, and it then behaves like that Turing machine. So if you take the thing that he called the universal Turing machine and give it input 257, it will behave like Turing machine 257. If you give it input 1009, it will behave like Turing machine 1009. And essentially what he'd realized there was something, a computer can be programmed to do anything. So the universal Turing machine is one Turing machine that can behave like any of the others. Now, the reason that he invented these Turing machines was to answer something called the halting problem. So I've stated this in slightly modern terms because it wasn't in terms of computer programs, it was in terms of algorithms. The halting problem says, given an arbitrary computer program or Turing machine or algorithm or something like that, and an input, determine whether the program will halt or run forever. So if somebody just gives you like some lines of computer code, it might finish or it might go on forever. So what Turing was after, or what people were after then, was looking for, some way of deciding this. And Turing proved there's no algorithm. It can't be done. There's no procedure to decide in advance if a Turing machine will halt or not. You've got to run it. If it halts, that's great. But if it keeps running, there's no guarantee that it won't halt in the future. It could run for 1 billion years and then finish. And this bit of work is what we're going to use to sort of define our ultimately random number. Okay, and this random number is called omega. Now, I say it's called omega. It actually depends on how you number all the Turing machines and how you encode everything. So it's sometimes sort of referred to as the omega constant or Chaitin's constant after the person who invented it, but it can vary. So it's really a whole class of numbers that you could generate in theory. Okay, omega then is the probability, usually expressed in binary, that a randomly selected Turing machine will halt. So if you can imagine, going back to our items in bags, having a bag that contained all the infinite number of Turing machines, and you root it in, pick one out at random, what's the probability that your randomly selected Turing machine will halt? Okay, that's a perfectly well-defined number. Okay, because some Turing machines halt and some don't, so there is an actual probability there. But there is no algorithm to calculate it. If there were, then we could use that to get an algorithm to determine if a Turing machine halts, and Turing proved that that was impossible. So omega is really interesting. My further maths group found this idea really interesting. It's a number, it exists, it has a perfectly good definition, but it's impossible to compute it. We can start estimating it. What you can do is you can get a sort of what's called an asymptotic estimate. So you can get a process where you keep approaching it from underneath. You can't approach it from on top, but you never actually get there, and you don't know how fast it's approaching it because you don't know what the actual answer is or anything like that. You can't use anything like that to actually determine what it is. Okay, so therefore there is no algorithm to generate omega, and it is, in that sort of algorithmic complexity sense, the most random number there possibly is. Okay, I refer to this as omega as Chaitin's constant. I'll just introduce you to another mathematician. I mostly picked this picture because he looks like possibly the coolest mathematician I've ever seen. This is Gregory Chaitin, who's an Argentinian-American mathematician. Interestingly, he's 1 year younger than Marilyn Vos Savant. They're nearly exact contemporaries. And he kind of lives in that bit of maths with logic and computability and verging into philosophy and things like that. Some of the things he publishes in philosophy I wouldn't necessarily say I'd agree with, about what maths is and that kind of thing, but he's interesting. He provokes a lot of questions and a lot of ideas. If anybody uses the plus maths website, he actually wrote a really good article about omega on there a number of years ago. You know, he's a really engaging writer, I think, to read, and he's somebody who certainly some of his stuff would be accessible to good, interested sixth form students. Okay, so that's all very well. You might say, are any common numbers actually random? That really all depends on what you mean by random. We've sort of had two definitions of it. We've had a kind of probability definition, you know, does everything have a nice even chance of having, are the digits in the right proportions, are all the kind of two digit strings in the right proportions of 3-digit strings, and so on. So anyway, just an example, let's consider the square root of 2. Let's consider the decimal part of that. Is that random if we just look at those digits? Well, in an algorithmic sense, it's definitely not. It's very computable because calculators find its digits easily. So, you know, in that algorithmic complexity sense, the square root of 2 is very non-random. In a probability sense, so in the sense of, you know, are all the digits randomly distributed if we look at probabilities of how things come up? No one knows. It seems like you would have to know this sort of thing, but this goes again to these idea of normal numbers, and there's very little known about them. I wish I could claim to more expert knowledge of this than I can. As far as I know, no one knows yet. Okay, last little bit for me, just to finish you off. I was talking about kiting and his ideas. Something that's slightly interesting. He expounds something that he calls digital philosophy, which might possibly impact on how we teach maths. The way we teach maths at school is very algebraic and very kind of solution focused and things, very, very step by step. Kiting's idea of digital philosophy says that we have to accept that there are mathematical facts that are true for no reason, that are true by accident. So he basically says that some things in maths, not everything, but that we have to accept that there may be things that don't have a reason behind them, and that this sort of obsession with explaining things may stop us seeing sort of other things which are there. He says then that maths must be investigated by at least partly experimental means. So we have to do things like looking for patterns in numbers, looking for randomness, looking for things that are there. Okay, so summary. Yes, everybody, it's the plenary. Okay, so just a few thinking points for you to take away from this, I hope. First of all, probability and maths in general is not uncontroversial. See your latest social media pile-on of anything to do with maths and science. Maths and mathematicians are connected to society. So not only are mathematicians in society and have to be responsible for what we do, but we should make this connection. Maths is related to things. Maths is related to what we teach in PSE. It has probability, it has risk, it has things that we can connect it to. A colleague of mine many years ago was responsible for developing our booklet that we handed out at open evenings. And the phrase that he used to describe sort of A-level mathematics, and he used a great phrase underneath it. He said, everything is connected. And I really sort of would recommend that sort of approach to anybody. My next thing, which I hope I've demonstrated tonight, is that weaving stories and random facts and things into mathematics teaching makes it vital and interesting. I realized I can see the number of participants, and you've all done really well in not logging off, even when I got to Turing machines, which are my personal obsession. But hopefully, you know, there will have been something in this which has sparked interest for people. Your students may not be interested in drawing sweets out of bags, but they might remember stuff about the Monty Hall problem, and it makes a connection with those students. And maybe my final thing, teaching that there are exciting and unknown avenues beyond the school curriculum can enhance our teaching and inspire our students, and hopefully inspire us as well. In those days when I'm bored of teaching probability or teaching percentages or teaching fractions, to sort of be able to read something and realise that maths really is that exciting thing that I loved when I was that fresh-faced student when I was 19. Makes me remember why I wanted to be a teacher and makes me know why I want my students to be interested in it. And all I can say to finish off with is thank you all very, very much for your attention. I appreciate you giving up an hour of your time on a dark November evening, and it's been a privilege to talk to you. And are there any questions?
Great, thank you, Andrew. That was a really fascinating and thought-provoking talk. I thoroughly enjoyed it. And no, you didn't have anyone drop out, just to reassure you. We haven't got any questions yet, but we have got a comment from John in the Q&A, which I think is going back to the probability misunderstandings near the start. So he's sharing one from a senior engineer. The probability of throwing a 6 on a dice is 1/6. Therefore, the probability of getting a 6 after 6 throws is 6 times 1/6, which equals 1.
Yeah, I'm sure anybody who's taught probability has marked that at some point as well. Yeah, there's actually a fascinating website, again, sorry to keep going on about this. I'll mention 2 of them, 2 more of my favorite websites, which probably illustrates how geeky I am. There's one called spuriouscorrelations.com, where it looks at random things. Just if you look at all the data in the world, you can find random things that correlate really well with each other. Things like the number of Nicolas Cage movies released and the murder rate in the United States, I think, have a very high correlation. And the consumption of cheese and the divorce rate in certain states. And the other one, I've actually found one, it's called something like probability misunderstandings. And it's somebody who collects probabilities and coincidences and things like that and publishes them. And again, they're a great source of sort of little anecdotes that you can use to illustrate teaching points with people.
That's great, thank you. We still haven't got any questions, but I've got a couple of questions, so I'm going to indulge myself and ask these, if that's okay. I suppose, firstly, I'm interested, you mentioned near the start that if you do further mathematics A level, you don't have to do statistics as part of further mathematics. And I was just wondering what your view is on the fact that you can do further maths without statistics.
I think I'm sort of like a kid in a sweet shop, really, is that the way that maths is kind of divided up for further maths. So the sort of the syllabus that we use, the sort of 2 compulsory pure core books, and then you have to pick 2 more from mechanics 1, mechanics 2, statistics 1, statistics 2, discrete 1, discrete 2, further pure 1, further pure 2. It's just like, you know, I'd love to do them all. I'd love to teach them all. I think it's kind of a shame if people didn't do further stats if they're doing maths. When I went to university, sort of maths, A-level maths came in sort of 3 flavours. You either did pure and applied, pure and stats, or pure and mechanics, and nearly everybody who did a maths degree did pure and mechanics. So I was kind of for about 4 weeks, I was kind of the stats whiz kid when I went to university because I'd done more than anybody else, but I was kind of the mechanics dunce because I'd done less. And I think really just the more exposure we can give, if people are going to university, what I try and do now is just sort of give them textbooks and say, you know, after you've finished your A-level, if you really like maths that much, read this. You know, it's interesting, and try and get them over that kind of hierarchy thing that I was so guilty of this when I was a student. Like, pure maths was there, mechanics was somewhere underneath it, and somewhere floating about at the bottom with my statisticians was statistics and probability. And this kind of everything is connected idea, which didn't really hit me until, like I said, I did probability measures in my 3rd year and realized suddenly I thought I was doing the purest of pure maths, and what I'm actually doing is the theoretical basis for probability. And I realized that sort of the key to everything was just sort of seeing these connections. And it does make me sort of wish maybe that I'd have done more applied maths or things when I was at university. But
That's
I
interesting.
kind of blinkered myself a little bit.
And I think we probably want them to be able to do all areas of maths, but there's limitations.
I think the other thing is you never know what's going to be useful, because when I did my master's degree, I ended up doing nearly all applied maths as well. So for odd reasons, but.
Okay, we've got a few questions coming in now for you. So RB, I think their initials, has asked, do you have ways to improve understanding probability, as conceptually I find it challenging at times?
I try to do experiments with people. So I sort of tend to find the nice one that I do with sort of year 7 or 8. Whenever you do teaching nets or something like that, I get them to make a cuboid at some point, and then I save these for my probability lesson later on. We always do sort of nicely equal things that are like, six-sided die and things like that. If you do a cuboid that's a sort of 2, 3, 4, so it's not too far off being a cube, but all the faces are slightly different, and you get them to roll it, you'll get something that's not equal. And in most classes, with a little bit of pushing, they come up with the idea that the frequency is related to the area of the side. If you choose your areas and choose the numbers, you make them roll it a bit carefully, you can make this quite suggestive. So also, I think, it's just the old sorts of things. If you've got time to do it, sort of a collaborative probability line where they sort of think about how likely things are that aren't calculable. So, we're in Manchester, what's the probability it'll rain tomorrow? What's the probability it'll be sunny in July? What's the probability that I'll have chips for dinner sometime this week, or something like that? And sort of just getting to think about those sorts of things without necessarily going into the details of calculating things. I think what we're all missing is we don't really have an intuitive understanding of probability, and that kind of talking about it and thinking about things and just sort of logically thinking about the situation a bit can help us to develop it. If anybody else has got better ideas, I'd love to have them, because I'll nick them happily for my lessons. I'm very well aware that my stuff could always use improving as well.
Thank you for that, Andrew. That was some really good ideas there. There are a few ideas popping up in the chat as well. I think what you just mentioned there about the weather links in nicely to Edward's question. Do you use examples like the weather or whether the bus is late to illustrate probabilities?
Yes. What I try to do as much as possible is to use sort of something like real data as much as I can. So, for example, we had buses late at school today. So if I could, like, next week teach probability, I'd say, okay, last week the bus was late 1 day out of 5, so it's got a 1/5 chance of being late or whatever. But then when I do that, you sort of have to talk about, even with year 7s, I think it's useful to talk about, well, we have made some assumptions here, and they might not fully sort of get to grips with it. But if you do that kind of every time you revisit probability, students, I find, as a secondary school teacher, sort of when they come in from primary, they like that kind of reassurance of there being sort of a solid right answer, and it's really quite hard to wean them off that. And it's kind of nobody's fault. It's a kind of comfort, I guess, as a child, that everything has a right answer, I can write it, I can get it right, or whatever. And to realize that, well, is it right? Well, what assumptions are you making? It's based on actually how you interpret things. It's a kind of level of maturity. So it's sort of almost, in math sense, entering the adult world and realizing that there aren't these sort of nice, safe answers for everything. And I think the more we can do to kind of ease students into that from early on, the better, really.
Yeah, I think that's a really interesting perspective, that as well. I think it's just turned 7 o'clock, so we'll stop the questions there, but thank you again, Andrew, for a really, really good talk. And thank you everyone for joining us.
Okay, thank you very much, and thank you again, everybody who attended.